Hi, everybody. I'm going to go over some rational expressions or rational polynomial functions with you and talk about zeros a little bit, just to make sure we're getting what we're supposed to get. So let me share the screen with you. So let's see here. There we go. And this is the handout, so we're going to go through it together. If it starts sharing, there we go. So what I'm going to do is I'm going to start with a polynomial. First off, I'm going to look at the end behavior. The end behavior and the leading term kind of go together. This is a cubic. The first term, if I'm in ascending order, or descending order rather, where we have a cube, a square, a first power, and then a no power. The leading term is x cubed. Number in front of x cubed is 1, so that tells it has positive behavior. Anytime you have a odd power polynomial, the end behavior goes down as we go left and up as we go right as we approach infinity. Okay, now when we look for rational zeros, this might not be all of the zeros. Zeros or roots, sometimes they're called, are x-intercepts. They can be called that as well. So sometimes when we go through, we don't find all the real zeros by doing this process. In fact, we might not find any real zeros, but this gives us rational, possible rational roots or possible rational zeros. Values for p are the factors for the last term here. That would be minus 16. So those would be plus and minus 2, plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8, and plus and minus 16. And then q, those are all the factors for the leading term. The coefficient of the leading term would be plus and minus 1. So p over q, when I take p divided by q, those are all the possible rational roots for this polynomial. So we take 1 over 1, 2 over 1, 3 over 1, 4 over 1, 8 over 1, and 16 over 1. And they're all over 1 because q is 1. We don't have any other worries with q, and it's plus and minus. So when we try each one out, we could either do this with the calculator, we could do it by hand. I strongly recommend you do it with the calculator. Okay, one way to do it with the calculator is set your table so that you can input the x under table set, which is the second function above window. Put into the y equal menu the actual function, and then hit second in table, and then input each one of these. So input minus 1, see what you get. Input 1, see what you get, and so on. Now, as it turns out, since it's a cubic, we can have at most 3 x-intercepts or zeros, and all 3 of these are found. One is found at minus 2, the other one at 2, and the third one at minus 4. So to verify that each one of these is a 0, we do synthetic division. So let's talk about synthetic division for a minute. So we'll start with the root minus 2. These are coefficients for the polynomial. So 1 in front of the x cubed, 4, minus 4 in front of the x, and minus 16 for the constant. I drop this first number straight down. I take minus 2 and multiply it by that first number. Put it here. Add these two together. I get 2. I take the minus 2, multiply by 2, get minus 4. Put it here. Add these together. I take minus 2, multiply it with the result of minus 8. I get a positive 16. Minus 16 plus 16 is 0. If this last number is 0, that means that there's no remainder. Incidentally, this is a polynomial in of itself. The answer here, that would be a 1x. That'd be a 1x squared. That'd be a 2x and a minus 8. Okay, and the same thing is true for 2. Drop the 1. 2 times 1 is 2. 4 plus 2 is 6. 2 times 6 is 12. Minus 4 plus 12 is minus 8. 2 times minus 8 is 16. 2 times 8, I'm sorry, not minus 8, it's positive 8. 2 times 8, I see I put a plus sign there. 2 times 8 is 16, minus 16 plus 16 is 0. And then we do the same thing with the 4. And here, our polynomial, our resultant polynomial, after we divide by the root of 2, is x squared plus 6x plus 8. And here it would be x squared minus 4. Okay, and then if I pick something that's not a 0, I go through the same process and I find there's a remainder. This last number is not 0. So the polynomial we would get here would be x squared plus 7x plus 17 plus 35 over, in this case, x minus 3. Okay. Since we got a remainder of 0 for each one of those are all roots. Now let's talk about the multiplicity. Since there are 3 zeros and it's a cubic, the multiplicity is, there are no repeated factors, so the multiplicity is 1 for each. What that means is that each x-intercept, the graph goes completely through the axis. So this is our end behavior. Down as I go left to right, up as I go right to, down as I go right to left, and then up as I go left to right. And then in between, I have a root at -4, -2, and 2. So that means I have to go through -4 up to some point. You know, I could estimate that if I put it in my calculator, okay? By doing a maximum, I could estimate that local maximum. But I really can't get an accurate value unless I know something about calculus. Then the same thing going down. It has to go through 2 and then come back to go through, it has to go through -2, then come back up around to go through 2. Let's try another. Let's try 2x to the 4th minus 5x to the 3rd plus x squared minus 4. The end behavior here, since it's even, just like a parabola, when I have a positive leading term of 2, x squared, or 2x to the 4th, when as long as it's positive and it's even polynomial, even powered polynomial, then it's going to go upward. And then going through the same process. Now in this case, I have a 2 for the leading coefficient. So the factors for 2 are plus and minus 1 and plus and minus 2. So that means I go through and I take each one of these p's, the factors for -4 in this case, and I divide by 1. So 1 divided by 1, 1, 2 divided by 1, 2, 4 divided by 1, 4. Okay? But then I have to do the same thing with the 2 here with the q. So 1 over 2. 2 over 2 gives us 1 again, so we don't need it. And 2 over 4 gives us 4 again, so we don't need it. And each one of these, again, is a plus and a minus. So when I try these out, I find that there aren't any zeros. I don't get a function value of 0 for any of those. So that doesn't mean there aren't any roots, any real roots or any real zeros. What that means is that none of them can be found that are rational. So they could have something like the square root of 3 or pi or something like that, some irrational number, but not one of these. Okay? So let's take a look. Let's go further. Let's put this into our calculator, if you will, and let's graph it. And we get something that looks like that. In fact, we have one real valued 0 here, but again, it's a irrational number. It's a number we can't get by using the rational root theorem. And so since that's the case, you know, we probably also have, and we have another one over here, so we have a second one that's irrational. So since that's the case, we probably have some complex numbers involved with this as well. Okay. Let's go through the third example. I think I have 4 examples on here. So the third example, we're looking at 4x to the 4th minus 4x to the 3rd minus 25x squared minus x plus 6. The end behavior again, it's a even ordered polynomial. Our leading term is 4x to the 4th, so it goes upward in both directions. And again, we look at the 6. The factors for 6 for p are 1, 2, 3, and 6, all plus and minus. The factors for q, which would be the factors for 4, that leading coefficient, 1, 2, and 4, all plus and minus. So we get 1, 2, 3, and 6 by dividing each one of those p's by 1. We get 1/2 and 1/4 by dividing by, and 3 halves and 3/4 by dividing by the 2 and the 4. That will then actually give us all the possible roots. And in this case, at most, we're going to have 4 real valued zeros or roots. And in fact, all 4 of them end up being rational. 0 at 2, there's a 0 at a half, minus a half, there's a 0 at f of a half, and there's a 0 at f of minus 3. And then when we verify, we do the same process. We put the root here, and then leading term, next term, next term, next term, and last term. Drop the leading term down, multiply it by the root, put it here. Add together, multiply by the root, put the answer here. Add together, multiply by the root, put the answer here. And then lastly, multiply by the root one last time, put the answer here, and hope you get a 0. In fact, we do. It's a little trickier with the -1/2 and a half, but it's still very doable. Okay? Especially when you have nice numbers like 4 times a half, which gives you a 2. And then when we graph this, okay, we have a root at -3, 0 or a root at -1/2, a 0 or a root at 1/2, and a 0 or a root at 2. And so I take a look at the end behavior. The end behavior is consistent with a positive leading term and an x to the 4th. I go through the 3, back up to 1 -1/2. I have to go through the y-axis, so it'd be helpful if I knew what the actual y-intercept was there. And in fact, we can find that by putting 0 in for x, and that gives us a 6. Then we go from there, we go down to a +1/2, and then back up around to 2. And again, this local minimum and this local minimum, we really have no idea what they are. Again, we could estimate them with the max or min key on our calculator. However, to really get those down, you have to take the calculus course. Okay? And then when we factor this, factoring is an important concept. Okay, remember when you factor it, when you put it in parentheses, you put the opposite sign with the root. So the -3 was a 0. But when I put it in the parentheses, I go x minus a -3, which is +3. The -1/2 was a 0. So I go x minus a -1/2, which is +1/2. And we had a +1/2, so that's x minus a 1/2. Then we had a +2, so that's my x minus 2. And then we have one more, I think, example here to tie it up. And this one's 2x to the 3rd plus 7x squared plus 4x minus 4. The end behavior is like consistent with an odd ordered polynomial. And so with a leading term of +2x to the 3rd. So we look at our p's and q's, divide them out, and we find we have a 1/2 of 1/2 is 0 and a 1/2 of -2 is 0. So for the 1/2 of -1/2, we end up with going through the process again, dropping a 2. 1/2 times 2 is 1. Add it to the 7, we get 8. 1/2 times 8 is 4. Add it to the 4, we get 8 again. And then 1/2 times 8 is 4 one more time. Add it to the -4 and get 0. And the same process goes through for the -2. And so we get 2 real roots. That doesn't mean there isn't an irrational one, or that doesn't mean one of these is repeated. When we get 2, you know, sometimes we might want to do a little investigation here, okay, and see if any of these repeat. So we should check to see if 1/2 or -2 repeated. To do this, let's first look at a 1/2, okay? And I'm going to take and divide out the 2, 7, 4, and -4 by 1/2. That gives us 2x squared plus 8x plus 8 equals 0, if you remember. Let's factor the 2 out. That gives us x squared plus 4x plus 4, which gives us x plus 2 times x plus 2. So that means x plus 2 is repeated. So when I factor this, it factors into x plus 2 quantity squared times x minus a 1/2 quantity, x minus a 1/2. Now this square means that the x plus 2 has even multiplicity. So what does that mean on the graph? Well, that means on the graph that when you go through this, okay, you hit that -2, it just hits it. It doesn't go through the x-axis, it just touches it at that point and then goes back down. Or if it was going down like this, it would just touch and then go back up. Whoops. And so it just goes up, 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 just touches the -2 and then goes back down and then goes through the 1/2 because it has multiplicity that's odd or 1. Hopefully this helps. Have a great day and we'll see you probably next week.